What do a campfire, a boiling cup of tea, these melting ice cubes, and the observable universe have in common? If you answer that they are all experiencing increases in entropy, you are correct. But what exactly is entropy? Entropy, usually abbreviated as S, is a measure of the number of microstates that a system can have. If you imagine the molecules in a cube of ice, they are packed together in a rigid lattice structure, and aren't as prone to movement as, say, liquid water, in which the constituent water molecules are more free to slide around. Since in the liquid state the water molecules have more freedom of configuration and motion, water has higher entropy than ice, and water vapor even more. Other rules that determine entropic order are molecular complexity, where higher complexity equals more molecular configurations and therefore more microstates, and increases in the number of moles during a reaction, which has the same effect. Given the difficulty of determining the microstates in a system, entropic changes are usually determined experimentally via calorimetry under standard conditions, that is, at a constant pressure of 1 atmosphere for 1 mole of the substance. Since the temperature is variable, it should always be specified. The change in entropy, or the entropy of a reaction, is essential for determining the spontaneity of a system, but to do so, we must understand a related concept first: enthalpy. Enthalpy, usually abbreviated as H, is the heat exchange between the system and the surroundings at a constant pressure. The change in enthalpy, or the enthalpy of a reaction, can be used to determine whether a reaction is endo or exothermic. Exothermic reactions, such as the combustion of the tinder in the campfire, result in negative enthalpy of a reaction. This is because the total energy of the products is less than the total energy of the reactants. This can be represented graphically, where the change in energy is greater on the product side, representing the energy released into the surroundings. Since this is a negative change in the system's energy, the enthalpy of the reaction, or the delta H, is negative. The opposite is true of endothermic reactions. Now, using our understanding of entropy and enthalpy, we are able to determine a third value, Gibbs free energy, usually abbreviated as G, which helps predict the spontaneity of a reaction. The change in free energy, delta G, is calculated by finding the difference between enthalpy and entropy. The resulting equation, known as the Gibbs free energy equation, is delta G equals delta H minus T delta S. A reaction is spontaneous if delta G is negative, and non-spontaneous if delta G is positive. Qualitatively, a reaction is spontaneous or exergonic if it favors the formation of products at the conditions under which the reaction is occurring. It is non-spontaneous or endergonic if energy input is required for the reaction to proceed in the forward direction and the formation of products is not favored. Using what we've learned, let's solve a problem. For the following reaction, calculate delta G. Additionally, determine whether the reaction is spontaneous, endo or exergonic, and endo or exothermic. Since we know that the reaction occurs at 293 Kelvin, the change in heat is equal to 19,070 calories, and the change in entropy is equal to 90 calories per Kelvin, we have all we need to solve the Gibbs free energy equation for this problem. After plugging everything in and solving for delta G, we have reached the number of negative 7,300 calories. Since change in Gibbs free energy is negative, it is spontaneous and exergonic. Since the enthalpy is positive, the reaction is endothermic.